Okay, apologies. Okay, sorry for that. Seems like my network went down. Okay. Good. So as I was saying, there was this paper. This guys, I hope you managed to listen most of that. You got most of that. So they tried to recreate the TerraSort challenge experiment in a lab environment. And this lab environment is what you would typically have if you were not like a huge enterprise. So like 5 to 10 machines connected with 100 megabit Ethernet, and having like, typical core counts, maybe 32, 64 cores per machine, and a few gigabytes, like 30 to 60 gigabytes of RAM per machine. That's what you might have, in a lab. That's what we have in our lab, for example. And what they saw was that actually MapReduce was much better than Spark in some of the tasks. And of course, that was a huge surprise. And it all boiled down to this shuffle phase. Because MapReduce did the map side pre-partitioning, pre-sorting, pre-combining, and put everything in one big file, that was what gave it the big push. So then they went back and they borrowed these ideas and they re-implement them in Spark. Okay, so these days data is automatically pre-combined in memory before written out, just like Hadoop MapReduce. Data is batched in memory before written, just like Hadoop MapReduce, and the output is no longer M times R shuffle files. Okay. Right. Okay. Shuffling is also pluggable, so you can define your own pretty much partitioner and shuffle implementation. The default is hash shuffling, just like in MapReduce, by the way. So this means that for every key you apply, your partitioner is a hash partitioner. So it hashes the key to get to a reducer ID. But you can also use a sort-based shuffling. And this is, we briefly discussed this a couple of weeks ago when we were talking about totally ordered output in MapReduce. So you can also do that in Spark, of course, and you can run your own partition or your own shuffle implementation. How about sharing state across executors? You don't really want to do this. You don't really want to have executors changing the same data item at the same time. Okay, why would that be a bad idea? Any suggestions? Integrity of data? Yeah. So if we say that this would jeopardize integrity, how would we guarantee integrity? What could we do to guarantee integrity? More use of network. Okay, good. Yes, I mean, if we want to share state across executors, we would need more network I/O, but that's not really the problem here. It's more along the lines of the integrity point raised earlier. I mean, if I have something, if I have an idea, like an algorithm in mind that needs to share state across executors, I need to pay the cost of the network. But what about that integrity thing, right? This all boils down again to these executors. If they cannot run in parallel, yes, we're getting somewhere here. So if these guys want to run in parallel and update that shared state in parallel, then they need to somehow synchronize with each other. Okay, and you may remember how many weeks ago we said that's the one thing we don't want to have to do. We don't want to have to synchronize across things that happen in parallel. Okay, so we don't really want them to have to do that kind of synchronization. So we have two ways. There are two ways that through which we can share state. They are called accumulators and broadcast variables. And if you if you reviewed the MapReduce material, this actually mapped directly to something we've seen, some things we've seen in MapReduce. Accumulators are updatable, shared updatable state. Broadcast variables are shared read-only state. Okay. So let's start with broadcast variables. These are the equivalent of Hadoop MapReduce's distributed cache. Okay, so you can use them to share read-only data across all nodes. Okay, so this is shared state, but nobody's actually updating it other than initially the driver. So what happens here is that, what could this shared state be? It could be some jar file or library or some other file required for computation. Example again, if you are doing some kind of like IR pipeline where you need to read your data, read some text data and throw out stop words and continue with your processing, you need to somehow communicate the list of stop words to your executors. And a broadcast variable containing all of those stop words is a very good way of doing it. Okay. And the way this works is that these broadcast variables are initially stored locally on the driver side. Okay. And the driver, first of all, serializes it. So it transforms that data from whatever state it is in main memory to some format that can be transferred over the network. And when there is a transformation that needs to use this broadcasted data, then this data is attached to the metadata sent to the executor. Okay, it's sent alongside the definition of the task. The executor will receive this, and then it will either first check its local file system to see whether it has a copy of the data. Okay. And if it doesn't have the data itself, right? So in the previous step, in this step here, the driver sends metadata. It sends a description of what this broadcast variable is, like a file with stop words. That's not what it will say. It will actually send a file name and plus information like file size and so on. So the executor will first check whether it has it already stored locally. Maybe it has it stored locally because it retrieved it for some task that was executed earlier. So it will check whether it's locally stored, and if not, then it will connect. It will connect to the driver over the network and copy it. Typically, this happens with HTTP transfers, but at some point, Spark also added torrent transfers. Now, I'm not sure how many of you are familiar with torrent. Don't even know if torrent is still around as a mainstream. Are people using peer-to-peer file sharing applications these days? I don't know. This was all the rage several years ago. So what is a torrent? Yes, but don't tell uni. Cool. Okay. This is not recorded, is it? So what is a torrent? Right. It's a peer-to-peer protocol, let's say. What happens is that if you have a big file to share, that big file is split into smaller pieces. And then, you have people that want to download that file from you. Typically, you would have more than one, right? So in this situation, if you have this broadcast variable that needs to be copied from the driver to all the executors, let's say you have a big cluster, you have like 10,000 machines. probably, let's say you have 10 cores per machine, then you would have 100,000 executors, right? All of them wanting to get a copy of that broadcast variable. Okay. So if you had like 10,000 or 100,000 processes connecting to the driver to get a copy of that, the driver would be overwhelmed. Okay. So what happens with torrent is that you actually sort of build a distribution tree, right? So some of these executors, some of these nodes, let's call them, will connect to the source, being the driver, and they'll start getting copies of some blocks. But then they will register themselves as having copies of those blocks, and other executors coming after them could, instead of copy that block from the driver, copy the block from whichever other executor has a copy of that block or of that broadcast variable. Okay, so in essence, you have your driver. The driver has sent a copy to some executors, but now the driver and the executors can all serve copies of that data. And the more copies you get in the network, the more sources you have for that. Okay, so in essence, the load is spread throughout all of the executors. Okay. I mean, this isn't super important. It's just an interesting optimization that Spark did to be able to broadcast this data in a more efficient manner than just HTTP transfers. Okay, and this data is, as a corollary of what we just said, it's transferred only once per worker node. So you spin up the worker node, you spin up the executor in the worker node, and the executor at some point will get this metadata that will ask it to acquire this broadcast variable. Okay, it will look locally. If it's not locally, it will fetch it through HTTP or torrent. But then once it is locally stored on the local file system, it is there for the duration of the life of the worker node. So it's not transferred again for per stage or per task. Why? I mean, of course, we don't want to transfer it. We don't want to transfer it multiple times to save network, but there's also no need to transfer it multiple times because this is read-only information. Okay, it won't change. If I get it at the beginning of my application, it will remain the same. That is the contract of a broadcast variable. Yeah. Okay. Someone says there, I mean, I wouldn't necessarily want to address this, but I will. Someone says that this sounds like the chaining of data and transfer in MapReduce between reducers. Well, it might sound like the chaining of data transfers between data nodes in HDFS, because in MapReduce, we don't have any chaining between reducers. So, I mean, of course, I don't know who made this comment because Slido is anonymous, but whoever it was, or if there are other people who have similar confusions, please go back and review MapReduce and HDFS, because this happens in HDFS, it doesn't happen in MapReduce. Okay. Okay. So that was broadcast variables, read-only. But now we have accumulators, which are updatables, writable. Okay. They are shared in quotes because they're not, I mean, they are shared in this way. They are created by the driver. So when the driver starts, it registers these variables. So all the executors know these variables exist. But what the tasks can do is they can only reset or add to an accumulator. Okay. So does this sound familiar? It should. This is the equivalent of Hadoop MapReduce counters. Okay. So every node, every worker node, so every executor pretty much, will I'll get that in a minute. So every executor can or will hold a local copy of this variable, and tasks will update that local copy only. Okay, so they can set it to 0 or they can add to it. And every now and then, when the executors communicate with the driver, or when the driver communicates with the executors, the driver can read the value and can accumulate the value, can aggregate the value over all copies of this value. Okay, so this is just like Hadoop MapReduce counter. Okay, but there are some quirks under failures. Okay, the contract that Spark gives us is that these are guaranteed to be updated once per action. Okay, so if we have a counter, sorry, an accumulator which we update as part of one of our actions, then it is guaranteed to be updated once for every split of that action produces, or for every item that action produces, if it produces one item. But there is no such guarantee otherwise. So if we have transformations that need to be restarted, or think of the speculative execution mechanism. If you have transformations that are started concurrently at many places, you could see these changes to these accumulators being applied more than once. Okay. If you restart a transformation for some split in your input, that will reapply any updates. Okay. They do not affect the lazy evaluation semantics. So having an accumulator does not trigger the execution of a job, right? They're not updated until the job is actually submitted for execution. But please keep this in mind, because I've seen this a couple of times in the past when people wanted to say count items in the input, and they would start a map, and then as part of their map they would update an accumulator. Map is not an action, right? So in the end they were getting the correct result, but only because none of their maps ever failed and had to be restarted. So just out of luck, right? So keep this in mind for accumulators. There is a comment about, I think the comment is about global variables, sorry, broadcast variables. And it says, I think it's like global variable which is static in nature. So in that case, can we broadcast some global function which can be accessed by all executors? Yes, one of the things you can broadcast is code to be executed. Yeah. Okay. Okay. Failure handling. So people have been asking about this in the past. So let's go through this and see what happens when things fail. RDDs, for every RDD, we get serialization error when we browse a method. Let's take that offline. Okay, let's take that offline. So for every RDD, we've said in the past that we record the lineage, and the lineage allows us to recompute the RDD from the source. So we had read from SCFS map filter. That is the lineage of that final RDD. So if something happens and we fail in computing one of the splits of that final RDD, we can always go back and do read map filter on the source data. Okay. We can also though take checkpoints. So at some point in time, say, okay, what do I have computed so far? Whatever, I want to somehow store it somewhere so that if I fail, at least I can continue from that point. Okay. Typically, going through the lineage path, so recomputing things is much faster, apart from a few cases, and that is when the lineages are very long. So if I have a long list of narrow dependency transformations that I need to apply to something, or if I have wide dependencies, because wide dependencies might need to recompute several things. I mean, in a wide dependency, you go up to multiple lineages of narrow dependencies, and you need to recompute all of them to compute your wide dependency output. So in those cases, it pays off, or it might pay off, to use checkpointing. Speculative execution is fairly easy due to RDDs being immutable. And I say this because you can start speculative execution tasks left and right. If one of them finishes, you keep its partition as a part of the RDD, and all other speculative execution instances, you can just ignore their output partition. You can terminate them and ignore their output partition. Okay. And no one will go and change that output partition that you kept from the winning task, because it's immutable. Okay, so what happens now with failures? If a stage fails, then that failure is detected and dealt with by the DAG scheduler. Remember now that we have the DAG scheduler sends data to the task scheduler, who runs tasks on the cluster. It gets back the results, propagates them to the DAG scheduler. So the DAG scheduler knows what happens where. So if a stage fails, then the DAG scheduler will know. Stage failure may lead to data loss or shuffle output files and this means that I need to recompute all of that stage, possibly. Okay, so if a stage fails completely, I need to resubmit it, recompute it. I might be able to save some of that computation if I have data like cached or whatever, but typically you would be recomputing the whole stage if it fails. Now, if you have a task that fails, okay, remember a task is one of those horizontal lines within a stage. So that is detected by the task scheduler. And the task scheduler would not need to annoy the DAG scheduler for that. It would just resubmit the task to an executor if it can be computed with no dependency on previous output. Okay. Now, if the driver fails, depends on what happens with, what mode we are running it in. If we run in local mode or in client mode, then the user needs to take care of that. The user needs to like restart the driver, restart the job. If it's in cluster mode, then the cluster manager will restart the driver. And this is the same as the application master, the MapReduce application master in Yarn. Okay, the cluster can restart it, but there are some caveats here. For this restarting to actually be supported, we need to make sure that the application master or the driver can maintain checkpoints of its state. Okay. If we lose a worker node, then that's handled by the driver and the cluster manager. Okay. So the driver will know a worker node failed because the cluster manager will tell it so, and the cluster manager will know because the node manager, the thing that the resource management infrastructure thing that runs on every node will inform the cluster manager. In that case, whatever tasks were scheduled on that worker node will be rescheduled on other worker nodes. And this is pretty much the same as losing a node manager in Yarn. And if we lose the cluster manager, then that's a much larger problem. This is the same as losing the resource manager in Yarn. Okay. Now that's pretty much the core of Spark. Spark also has a bunch of built-in libraries. It has libraries for streaming. We said last time that it's not a real streaming thing. This is using micro batches, and each of these micro batches is treated as a micro RDD. So what the driver does is start these long-running tasks that read and replicate the input data, and then every now and then it will push a DAG of operations to ingest the next micro batch and the next micro batch. There is a built-in library for SQL that uses data frames and data sets these days. I think that in the lab, you're probably using data frames and data sets, not RDDs directly. Whether you should go for one or the other can be a long discussion, but we can have it on the forum if you want. It uses a full-blown query optimizer called Catalyst, quite a bit of software, very, very interesting. As of the time of writing of these slides, Catalyst was not as mature or complete as Hive, and this SQL was not as mature or complete as Hive. I think that this has changed these days. So 3.2.1, whatever version Spark is out now, I think it now has a much better, much more complete implementation of SQL. But Hive can also be retrofitted to use Spark instead of MapReduce or instead of Tez. So you can combine both. There is a library for machine learning applications, machine learning algorithms. And MapReduce had one of these guys called Mahout, but Spark's MLlib is almost as complete and typically much faster than Mahout over MapReduce, over typical executors. There is a library for processing graphs. This tries to do typically the same thing that Giraffe and Pregel do. Spark also comes with its own serialization to serialization framework called Tungsten, which allows it to do many of these things very, very quickly. Hey. Okay, so this is an example of the word count here. We're running out of time. I'll just go through this quickly. So what do we do here? We create a Spark context object. So this is a context created on the basis of a Spark conf object where we just set the name. In this case, you could be setting other parameters for the Spark conf too. And then using this Spark context, we do a bunch of things. So we .text file, whatever. We read a file, in this case, from, let's say, HDFS or the local file system. This is a transformation that defines an RDD. So the output of this guy is an RDD, as we discussed it earlier, where the input is a file from HDFS or local file system. And then we flat map that. So on that RDD, we apply another transformation. And in this case, it's a flat map transformation where for every string in the input, for every line in that file, we split it on spaces. So we, assuming the file is well formatted, this creates a list of words in the file for every line. And then we map to pair. So for every word in this list, we create a tuple with the word being the key and the value 1 being the value. And then we reduce by key, right? So all of these would be grouped together by the word, and the values, we would take them 2 at a time and add them up, okay? And remember, this happens iteratively. So first and second value are added, the result of that to the third, the result of that to the fourth, and so on. So in the end, we get something that has a word and the sum of the counts, and then we save as text file. This is the action that would trigger all of this being executed, okay? So if you try and execute this on the cluster, or maybe even on the local machine, you can see something like this coming out of the web interface of Spark, okay? So this defines all of the RDDs and the dependencies, and you can see that I have the text file. I start from my input file, I apply the text file transformation, I apply the flat map transformation, I apply the map transformation. This is the map to pair. And then I have a reduce by key, but the reduce by key is a Y dependency. So this is where my first stage finishes and my second stage begins. And then I have a save as text file. This is an action, but it's pretty much an arrow dependency here for every split. And in this RDD, I will create something in the output. So this is in the same stage, and that's how this will be executed. Okay. If we have, yeah, and you can you can get even more information on exactly what file is executing or what file is defining all of this, right? This is all on the web interface of Spark. But with something like PageRank, I won't go through this, we don't have the time, but I'll just say that depending on how you write the code here, like when you do caching, where you do joining, where you do group by key, where you do distinct, and so on, you could end up with something that looks like this, a DAG that looks like this, or a DAG that looks like this. I don't have the source code of these two handy now. I can pull them up. The changes between the two are minimal, like 1 or 2 lines of code. But you can see that this second way of executing this, the second way of expressing the graph results in 6 stages as opposed to 8 stages in the top. And in essence, in actuality, this bottom code runs twice as fast as the top code, doing exactly the same thing on exactly the same data, right? So it's one thing to write code in Spark that does something you wanted to do, like compute a map reduce, sorry, a PageRank. And there's a different thing to do it in a way that is efficient, right? And I hope that you'll have the opportunity to explore this as part of the labs and the assessed exercises. So I'll stop here. I'm way over time. Apologies for keeping you later than I should have. And now, if you have any questions, please ask them on the forum. I'll be going over the forum daily until the next week. And if not, next week we'll be moving away from execution and starting looking into NoSQL stores. Okay. Good. Thank you all very much. Have a nice day and a nice weekend. And see you all next week.
Thank you, Professor.
Thank you, Professor.